Welcome back to the session. Today we have Mr. Shaw Wheely with us. We'll be discussing high cycle fatigue and ultrasonic fatigue modeling using unified mechanics theory. I welcome Shaw to continue his presentation. Shaw, are you ready?
Yeah, I'm ready.
Thank you.
So thank you for everyone's participation. So today I would like to continue from yesterday's lecture. Today my topic will be the modeling of ultrasonic vibration fatigue life with unified mechanics theory. So let me start my slides. Okay. So this research is actually a collaboration research between 3 different groups. We have me and Professor Bastrong at University of Buffalo, Professor Egna, Professor Lipsky, Dr. Michael, and then Moraski at Poland, and of course Dr. Nashad and Professor Rao at India Institute of Technology. So these 4 researchers are from Poland. They are doing a collaboration research with us because they are the only one who have the ultrasonic vibration machine. So they are responsible for the experimental research part. So this introduction about the unified mechanics theory I already summarized yesterday, so I will skip this part. So for the ultrasonic vibration fatigue of the metal, the frequency is of course different than conventional tension compression hydraulic machine. We have a frequency around can be up to 20 kHz to 30 kHz. Under this high frequency, we will have a frequency effect and high strength rate effect. We have to consider in the entropy generation mechanisms. And still, ultrasonic vibration fatigue is essentially another way to produce a large amount of cycles in a short time. So it is still belongs to a high cycle fatigue. So it means that the yield stress, of course, have to be below the nominal stress have to be below the yielding stress. And again, there's no macropassive deformation. These are the 6 important micromechanisms I mentioned yesterday. We have this configuration entropy, vibration entropy, entropy generation due to a diffusion of atoms, thermal conduction, internal frictions, and microplasticity. So among these 6 mechanisms, the entropy generation due to thermal conduction, due to internal friction and microplasticity actually will be strongly affected by this frequency. Because this one, thermal entropy generation due to thermal conduction, when we have applied the ultrasonic vibration to the samples will have a larger temperature increment compared to the conventional high cycle fatigue. For example, in a conventional high cycle fatigue, the temperature difference between the center and the edge may at most around 15 to 20 Kelvin. However, in the ultrasonic vibration fatigue, the temperature difference can be goes up to 100 Kelvin to 150 Kelvin. So that's create a larger temperature gradient. And therefore, the thermal conduction entropy production will be therefore larger. The next one, entropy generation due to internal frictions. Yesterday, I ignored these mechanisms because these mechanisms will not have significant effect in the low frequency range. However, when we talk about the ultrasonic vibration fatigue, some mechanisms like the drag of the phonon, drag of the electron, drag of the radiation, they comes into play in this high cycle condition. And also the dislocation, displacement, relative motion will also cause entropy production. So this one have to be considered in this test scenario. And finally, microplasticity entropy production also have some changes because this microplasticity will be affected by there will be a frequency effect that affects the production of microplasticity. So these 3 are the mechanisms we have to go over again. So before that, I would like to first quickly go over the test setup. So this one is our test sample. All the diameters are in millimeters. So you can clearly find that this is actually a very small sample, only about 6 centimeters. And this scale sample is equivalent to the A656 grade scale in the United States standard. And it has a very specific geometry. These geometries has to be designed in very specific details so that they can create the required resonance frequency. The fatigue tests are performed on the ultrasonic resonance test machine with a stress ratio of -1. Of course, the frequency is around 20 kHz. We apply the vibration amplitude of 60 μm. During the test, we use a thermographic camera to capture the temperature variation, focusing on the gauge center. Because we know the temperature increase in this ultrasonic vibration fatigue will be very different than the conventional high cycle fatigue. So we would like to monitor this temperature, and then we derive another thermomechanical equation. We are trying to compare the simulation data with the actual monitor temperature. So that's the reason we set up a thermographic camera here. So actually, we have to do a model analysis finite element to carry out the frequency, to find the natural frequency, resonance frequency of the sample in the actual direction. So basically, we build up a Abacus FEM software and then perform these steps, tension conversion resonance frequency in the actual direction. And we figure out that the frequency is the resonance frequency is around 20 kHz. It is actually only about 1908 this amount of hertz, very close to 20 kHz. And here you can find the stress distribution and the displacement distribution of the sample. So this the test is actually consists of 3 different parts. So first we have this component called the booster. Booster is used to generate a vibration amplitude, a displacement amplitude in here. And the ultrasonic energy is transmitted from this booster to this home all the way to the final sample. So this is our sample. And you can see we have a larger stress amplitude here, and the stress amplitude here is of our interest because we are interested in the stress amplitude at the gauge section. So this one is the distribution of the stress. This one is the distribution of the displacement. So this is a model analysis with finite element simulation results. We can find the average stress amplitude around the gauge center. This one is on the surface. This one is the cross-section view. And this one shows the average stress of around 380 megapascal with applying stress amplitude with applying displacement amplitude about 0.018 millimeters. And this one shows you the profile of the stress and the profile of the displacement. And again, this stress amplitude is the stress amplitude at the gauge center, and this value must not exceed the yielding strength of the material. The yielding strength of the material, I remember, is around 400 megapascals, 400 to 410 megapascals. So the stress amplitude here we have to control it and cannot let the stress amplitude at the gauge center larger than the yielding strength. So this is our ultrasonic resonance testing machine, and this one is our infrared thermographic camera. We use a total of 21 samples to determine the fatigue limit, and we use another 15 samples to construct the fatigue SN curve. And among these 15 samples to construct the SN curve, we monitored 11 samples. We use the thermographic camera to monitor 11 samples. the temperature are recorded and can be shown in the later picture. So this one is the staircase fatigue data obtained from the experiment. They use this so-called up and down method. I believe this one is a statistical method to interpret the data. And finally, using Dixon formula, another statistical method for the experiment, they find that the fatigue limit is around 368 plus and minus 3.3 megapascal. Plus and minus 3.3 is basically just a standard deviation of the fatigue limit. So they determine the fatigue limit by experiment using these two statistical formulas. And finally, this one is the fatigue SN curve for the ultrasonic vibration test. The first line is 95, I believe the 95-degree confidence level, and the other one, anyway, and these fatigue data are forced into the different confidence level. And this one shows the temperature evolution on the surface of the sample using the thermographic camera I showed you before. So this temperature is actually quite important because, as you can see, unlike the conventional high cycle fatigue usually have an initial increase of temperature, and all the way it will keep and maintain as a constant temperature. However, in the ultrasonic vibration fatigue, we have an initial high temperature increase followed by a almost linear setting temperature increase in this part, and finally rapid temperature increase in the final stage. So actually this temperature evolution can be divided to 3 different phases. We can say the first rapid increase part is a phase 1 due to internal frictions, and it is increased very fast because it can be achieved in only several seconds. And that in those only several seconds, there's not enough time to actually activate this heat dissipation. So initially we have very high temperature growth, very rapid temperature growth. And in the phase 2, which is this approximately linear stage, we have a steady heat generated due to internal frictions, microplasticities, and we also have a local heat loss due to the conduction of the heat with the environment. So we have heat at this stage, we have a steady increase of temperature. And finally, this part, again, this rapid temperature growth part at the final stage is what we call phase 3. At this phase 3, we have a very rapid temperature increase due to the initiation of micro cracks. So that's the 3 different phases of the temperature profile during the ultrasonic vibration fatigue. And here I'm showing you the temperature distribution on the surface of samples at different phases. This one is at the end of phase 1. These two are middle of phase 2, end of phase 2. And this final figure is the end of phase 3, which is the start of cracking. So actually, we can find that even though in the phase 2, even though phase 2 temperature gradient is much lesser than the temperature gradient in the phase 3, we still have around 80 to 100 Kelvin temperature difference between the gauge section and the grip section. So the temperature difference is actually already very high for the ultrasonic vibration fatigue, even though it is in the only in the phase 2. So the temperature difference between the gauge section and grip section is already around 80 to 100 Kelvin in the ultrasonic vibration fatigue. It is very large compared to a conventional high cycle fatigue. So that's the experimental part. Later on, we are trying to use the thermomechanical equation, trying to rebuild the temperature simulation data and compare our similar temperature simulation data with this experimental curve. And we are also going to use unified mechanics theory to build up a SN curve and compare our SN curve with this experimental data. So these are the 6 entropy generation mechanisms I mentioned yesterday. So these 3 mechanisms I have already explained, they are actually quite small compared to the other 3 mechanisms. So these first 3 are negligible in our case. At least 4 mechanisms are mechanisms we have to study in this paper. So the entropy will be composed mostly of these 3 mechanisms: thermal conduction, internal heat generation, and microplasticity. So these are configuration entropy, vibration entropy, and vacancy concentration, all explained, introduced yesterday. So again, this one will be the entropy generation due to thermal conduction. The value will be higher because the temperature gradient will be higher in the ultrasonic vibration fatigue than the high cycle fatigue. Now the drag mechanism, we have the internal frictions. In this case, we have to start considering initial internal frictions because in the ultrasonic vibration fatigue, there's a mechanism called the drag process that involves the phonon drag, electron drag, and radiation drag. And we figure out that at this frequency, the phonon drag is actually the most dominant dragging mechanism among these 3. Basically, at a high strain rate, in addition to the dislocation to dislocation interactions, we also have these mechanisms resulting in a viscous drag. This viscous drag is due to the interaction with phonons and the dislocations. So these thermal phonons in a crystal are scattered by these sliding dislocations. When there's a dislocation movement, the phonons will basically provides impedance force, and that will in this case it will resulting in a drag force, and that will lead to the energy dissipation. So the total internal heat generated rho density times the amount of heat generated per mass during the drag due to the drag mechanism is equivalent to the total dislocation density times the dislocation drag force per unit length times the velocity of the dislocation. And the drag force per unit length of the dislocation is equivalent to this drag coefficient B drag, again times the velocity of the dislocation. So this the total density of the dislocation times the force per unit length gives us a total force, and again force times the velocity gives us the work per unit time. And one thing we have to be careful, I have to emphasize here is that the dislocation density is actually closely related to the shear strain rate. So this term is actually strain rate dependent. So strain rate will affect the contribution of this equation. So this term, drag mechanism, is strain rate dependent. Another term, the dislocation relative motion during the microplastic deformation, is given in this term. In this term, we also have a shear strain rate term. So combining these 2 equations, the first drag mechanism, heat generation due to drag, phonon drag, and the heat generation due to dislocation motion, by combining these 2, we find the amount of entropy generation due to the internal heat generation will be this combination of these 3 terms, and they are strain rate dependent because V is related to a shear strain rate, and this one is also related to shear strain rate. So the shear strain rate affect this term. In a ultrasonic vibration fatigue, we have high strain rate and high frequency, so this equation have to be considered. Finally, the entropy generation due to the microplasticity. Basically, this 2-scale model I already explained yesterday. We use the laws of localization to find the micro stress and micro strain at the corner of the inclusions. These all calculation mechanisms are the same. The only difference is that in the ultrasonic vibration fatigue, I have to add an additional coefficient called the frequency calibration coefficient to our equation. So let's go over this equation again. So This equation have a micro stress tensor product microplastic strength, micro stress times a microplastic strength. That will be the microplastic work divided by the temperature, work divided by temperature. That will be the entropy per unit time. Times the FV. FV is the volume fraction of the micro defects, because we're only accounting for the microplasticity. Microplasticity happens at the micro defects. So we have to times this FV coefficient. Phi is accounting for the evolution of the micro defects, evolves from 0 to 1. So far it is just the same equations as I mentioned yesterday. However, here I'm adding another coefficient called the VF. VF is a frequency coefficient. So what this coefficient do is it relates the frequency effects to the entropy production rate. As we know, some materials, if we give it the same stress amplitude, but operating them at different frequencies. For example, we give them the same stress amplitude around, for example, 380. However, we are operating them at 20 Hertz and 20 kHz respectively. There will actually be a fatigue life difference between the 20 Hertz and 20 kHz. That's the frequency effect. And this coefficient is used to calibrate that effect, to consider that effect actually. So this coefficient is used to rate the machine operating frequency with the entropy generation rate. So this to study this coefficient, we have to look inside the details of the structure of our material. So our material is basically a ferrite-based structure steel, and for ferrite-based steel and have a BCC structure, we have a transition between the deformation fault from this thermally activated region to a thermal mode at stress amplitude above the fatigue limit. So there's a transition between this region, between these two deformation patterns. And these two deformation patterns actually have different micromechanisms. For example, at least at thermal mode, which is where our ultrasonic vibration belongs to. At this mode, we have a mobility of this the mobility of screw and edge dislocation will be equivalent, as screw dislocation can cause slip. So the micromechanisms here is the cause slip of screw dislocations for the ultrasonic vibration fatigue that belongs to this region. So this the cross slip of this screw dislocation is actually frequency dependent. It is frequency dependent. As you can see, this one is an equation obtained during the literature review. I find that there's actually a cross-slip probability for the cross-slip probability of the cross-slip dislocations, or cross-slip of screw dislocations. It is related to a coefficient, the relative length, the duration of the time versus the reference time, the resolved shear stress minus the critical shear stress that can activate the cross-slip over a Boltzmann constant, absolute temperature, and the volume of the screw dislocation. So this one is a probability, cross-slip probability for screw dislocation. And by this probability equation, it can be further derived. We can further derive this equation to obtain the time duration to activate one cross-slip. That will be this equation. And the time duration to activate one cross-slip is inversely related to the operating frequency of the machine. As you can see here, it is inversely related to frequency. So now, for example, if we have the same stress amplitude, we give the test sample the same stress amplitude, but we are operating them at different frequency range. One is around 30 Hz, the other is around 20 kHz. In order to reach the same cumulative probability of cross-slip activation, in order to make their probability the same, the time duration to activate the cross-slip per cycle times the total amount of cycles must be equivalent. The multiplication of this time and the number of cycles must be the same. So we have this equivalent equation. So we can assume we can obtain a approximate relation between the numbers of operating cycles and the numbers and the frequency and the operating frequency. The number of cycles to reach value is actually positive related to the operating frequency of the testing machine. But again, this equation is only applied to the ferrite-based metal, because for ferrite-based metal, we have this kind of transition mechanisms, and we have this kind of school duration quantity. So that is restricted to that case. So by obtaining this positive relation, we use this fire factor to include above frequency effect. The fire factor is basically approximately the conventional operating frequency divided by the ultrasonic vibration frequency that is used to include the frequency effect. So everything is the same here, but the only difference is that in the microplasticity model, we add the frequency coefficient to our entropy generation equation, because under different amount of frequencies, for example, under the ultrasonic vibration for at least 20 kHz, we'll need more time to actually generate the microplasticity. Yeah.
Sorry to interrupt you.
Yeah.
Can you explain what is cross-sleep?
Cross-sleep, I don't have a picture here, but it is two dislocations. They kind of cross-sleep like this. They have an angle that basically one dislocation is in cross-sleep with the other dislocation. This kind of direction. I can show you maybe a picture of the cross-sleep after the presentation. So that will be the only difference between our model, our previous model and the current model. The microplastics have to include this frequency effect to the microplasticity entropy generation. So then we have this thermodynamic fundamental relation in metal ultrasonic vibration for the that will be the specific entropy production of in our system. And these three terms are this turn, and this turn. These three terms are the dominant mechanisms. And we can use the specific entropy production, implement this one into our TSI equation to calculate the evolution of this index. And similar to the previous lecture, the surface of the temperature T must be investigated in detail in order to precisely obtain the entropy production, and that can be reached by deriving this thermomechanical equation. The thermomechanical equation is again derived from a traditional is derived from conventional continuous thermomechanics, continuous thermodynamics, and we are replacing the passive work by the micropassive work, and we are also introducing the internal heat generation from the. We are also introducing internal heat generation from the dislocation and the drag mechanisms here. We will include the heat generated from the internal frictions into our equation. So this equation will be the thermomechanical equation that can help us to simulate the temperature. And we can discretize this equation to find the time integration form for the temperature. And we can also find the temperature increase per cycle. So this temperature equation is used to help us to find the temperature inside this entropy generation equation. So these are material parameters for the material. These are material parameters for the dislocation motions. And finally, we have the entropy generation versus the amount of cycles. And here, at this time, I'm showing you all the stress amplitude versus the all the entropy production from different stress amplitude. We have around 1, 2, 3, 4, 5. We are around 7 different sets of data. We are all running them and trying to test their frequency, and they at failure they all created the same amount of accumulated entropy. This entropy again is called the fatigue threshold entropy, and the fatigue threshold entropy is depending on the material, not the geometry, not the test frequency, or not the loading type. It is related to material. So the fatigue threshold entropy for this material is around 4.1. And finally, we have the temperature and TSI evolution. So these curves that have the arrow is the experimental obtained temperature, and these lines are the temperature, the simulated temperature. So we can see that actually the simulated temperature can match the experimental data in phase 1 quite well. A little bit difference in the phase 2, and it cannot capture the phase 3 because in our thermomechanical equation we are not including the evolution of the cracks. So of course our thermomechanical equation cannot simulate the phase 3. But because phase 3 also includes a lot of instabilities, so it is very hard to simulate this part. But since this part only contributes a very small amount of fatigue life, so it is okay to ignore the phase 3 temperature evolution in the thermomechanical equation. And finally, this one will be the thermodynamic state index evolution from 0 to this given number. So we can use the stress amplitude versus the number of cycles to reach failure to again reproduce a SN curve. And this time we can see our SN curve in this line. And it is forced in this confidence level. So that will be how to use a unified mechanism to model ultrasonic vibration fatigue of a material. So the conclusion will be we derive the thermodynamic fundamental equation and use the thermodynamic fundamental equation to implement to our thermodynamic index to calculate their fatigue life. However, the only difference between the high cycle fatigue and ultrasonic vibration fatigue is we have to consider the frequency effect when in the generation of microplasticity, and the frequency effect and the hydrogen rate effect were also causing the heat generation from internal friction. These two are main factors that will basically change the fatigue life between these two different tests. So thank you for your listening.
Thank you, Shao. Now I will request the participants to pose questions if they have.
Can I ask the question, Shigo?
Yeah.
It's a very good presentation. I just want to know that the temperature we are probing on the specimen, this is related to the temperature on the specimen.
You mean
yeah, so what I want to know is
you mean a material constant?
Yes. Fine.
Oh,
no.
Yeah.
No, temperature.
Okay.
Temperature.
Yeah.
This is fine.
Yeah.
This slide is fine.
Yeah.
No, where you are measuring the temperature, that whatever figure you have shown now, no? Temperature distribution on the specimen as a function of number of cycles.
Oh, this one? This number of cycles?
Yes. So
Yes.
here, because the test is done in open atmosphere, right? it is done in ambient environment, open air, correct? Because the environment is not. That means there is a. It's not a adiabatic type of. What I mean to say is that the actual temperature that that may be generated may be higher than what is measured because of dissipation. Is it true? I want to know whether it can be higher than what is measured here because of dissipation to the surroundings. The temperature what we measure on the specimen may be lower than what is actually generated, or no? I just want to know that. Okay, I will put it again.
Yeah. Yeah.
This is a temperature measured by the measured temperature.
Camera.
Yes.
Yes.
But during deformation, because of heat dissipation to the surroundings,
Yes.
the actual temperature may be higher than this, or no?
I think during the testing, I believe that during the testing they are actually monitor the temperature by this machine, right? So this machine they monitor the. Oh, okay. So I see your question.
This is after the heat dissipation we are measuring, right? There is also a parallel heat dissipation is going on to the surrounding.
Yes. Surrounding. So
the temperature will be higher than what we measured, right?
But I believe the temperature they measured is the instantaneous temperature they observed at the gauge section.
Okay. Okay.
So that's this instantaneous temperature. For example, it is consistently under a psychic loading, and they are consistently using this camera to monitor the instantaneous temperature change at this center during the entire testing. So they are not allowing these samples to have a cool down period. This is a continuous. I believe this is a continuous process.
Okay. Okay.
Yeah.
So fine. So then, do you know the frequency? Say, for example, if you consider two slip planes, okay, each slip plane is having one dislocation, like slip plane 1, and parallel to that another slip plane. Okay, so there are two dislocations on the two slip planes. So because of very high frequency, it is possible that they may not see the presence of each other. Like one dislocation is approaching another dislocation, but they don't feel the interactions because the frequency is very high. So they may see only the lattice drag, that is, lattice vibrations will cause the drag for the dislocation movement. So what is the cutoff frequency usually where the dislocation doesn't feel the effect of another dislocation? Did you consider that? Is it because the frequency is very high? We are in the viscous drag region, I feel.
Oh, you mean the frequency that will actually activate the frequency?
The frequency when the dislocation, there are two dislocations. So, but they will not see each other because the frequency is very high. But they may see the lattice vibrational drag. So there will be some cutoff frequency between these two. That means below certain frequency, lattice drag will be there, plus dislocation interaction will be there. But above certain frequency, only phonon drag will prevail. So that is something is there on this. Maybe it may not be there in the frequency what we tested. Very high frequency, it may be there. Okay. So then another question is this: what do you expect the cracks where it will form? You feel that PSB persistent slip bands play a role, or because PSBs will form on the surface, correct?
Yes.
Whereas near the inclusions, PSBs may not be there.
Yes, so you mean PSB is extrusions on the surface?
Yes. Yes, it may be there, but when we are doing it very high frequency, you also observe PSBs on your specimen. It will be there, no? On the testing specimen.
I believe it may not be shown on the surface of samples because according to the transition in also a very high cycle fatigue, sometimes the failure is from the inclusion induced failure, so we may not see the extrusion of the sequence on the surface.
Yes. So your material is failing by inclusion induced failure, right?
Yeah. Right.
Okay. Okay, thank you. Thank you very much.
Thank you.
Hello, Lee. I have
Yeah.
a query. Thanks for continuing the yesterday's nice lectures.
Yeah.
Now I am gaining more insight in this UMT model. Just I was thinking that you have proposed the at least I think 5-6 the entropy is source of they contribute in the failure.
Yes.
So which one is most significant? Is there any order sequence or ascending or descending order? One can say that this particular factor has more contribution in failure. You have done that type of study?
Oh, you mean the comparison between different mechanisms to see which one have the larger
Yeah,
contribution?
the different mechanisms which you have just
Yeah.
explained.
Yeah, so actually the contribution here will be let me see. So these two are basically in the it can be negligible. One is the configuration, the other is the vibration, and these diffusion mechanisms can also be ignored. So these three will actually controls the total entropy production. But among these three equations, I believe the internal frictions and the microplasticity will be higher than the entropy production of the due to conduction. So these
Right.
two will be, yeah. So this, if you want to use the model, then we can simplify our equation to just include this one, and this one.
Thank you.
Yeah.
Thank you, Dr. Singh. Any more questions? I think I should call by name. Mahendra, you were asking one question about cross-link mechanism.
Actually, he answered.
Yeah, answer no.
In the middle of the presentation, the question was answered.
Okay, fine.
I have a small query. How do you subject the specimens to ultra high frequency vibration?
So,
is
okay,
there a
so-
special machine you have for that, or?
So we basically, at least is our machine, right? So we are generating actual resonance. We apply the actual displacement in this actual direction. So there's a displacement in this direction, and it lets the specimen to vibrate at this resonant frequency. So there's actually the samples here. The samples I show you here. Although they already have a given dimensions, but actually these samples have to be designed in very specific details to allow it has a resonant frequency around 20 kHz. Then we apply the actual amplitude in this direction to vibrate the samples, try to reach its resonant frequency. When it reaches resonant frequency, then it will be vibrating in 20 kHz. And we can see the stress distribution and the displacement, stress amplitude and displacement amplitude when we actually vibrate the samples at that frequency.
So the machine can vibrate at that frequency. That's
Yeah.
okay.
Any other questions? Brahmadatan, are you speaking?
Yeah.
Your voice is feeble, not clearly audible.
You can write in chat box, I suggest.
Yeah.
Meanwhile, I want to convey one information. People are joined. So all the people who are joined through AICTE, we have sent you one email regarding the confirmation of your details. Please acknowledge that so that we can prepare your certificates. Those who have joined through ISAM, we will prepare your certificate separately. But for AICTE, the certificate should be issued by the Center of Continuing Education, IIT Madras. For that, you have to verify your details. So the mail has been sent today. Please verify that, I acknowledge that, and then we can start preparing your certificates. Thank you.
Thank you, Ashish.
Thank you.
So, any more questions?
Hello.
Hello.
Can you hear me now?
Yes. Yes.
Actually, you mentioned that 6 entropy generation mechanism. Is that
Yes.
limited to this particular material, or is it common for same
All
kind?
metallic. Yes. In the equation here. Let me see. Yes, and this thermal conduction equation is for all the molar material. Applies for all different materials, but we have, of course, we have to change the conductive coefficient. This one applies to all the materials because it is about the permutation of atomic different size. This one also applies for all materials, but I believe the only difference, the biggest difference here is the generation of microplasticity. Because here we are adding the frequency coefficients to our equation, and that may not be true for all different metals. For example, if your metal is a martensite-based metal, then it will not have a significant frequency effect. It means that when you apply, for example, 20 hertz and 20k hertz, the fatigue level will be approximately the same. But for some materials, there will be subject to the frequency effect. So that will depends on this equation. This VF factor is actually depending on different kinds of material. But the rest of the equation, I believe it can be applied to all metallic material.
So if we consider different range of frequency, so this 6 mechanisms will come again.
Yeah. So only for some specific materials we have to consider frequency effect, and for some materials we don't, because their micromechanisms doesn't contribute, doesn't have a relation between basically the frequency effect will not affect their micromechanisms. So some materials don't have to consider this effect, but some materials have to. So that will be a material dependent parameter, this one. And the other sources are basically universal for the metallic material.
Dr. Lee,
Yeah.
are you planning to work on Paris law using this methodology we have developed for SN curve and all?
Sorry, for what?
Are you planning to work on the Paris law using the methodology you have developed now?
So use this methodology to do what? Sorry.
Paris law.
Can you write in the chat? Thank you.
He's talking of Paris law, which is used for crack propagation.
Oh, crack. Oh, okay. Yeah, so that will be an interesting topic, but currently this equation cannot be used to predict a crack propagation, because we are not including that mechanism in our equation. But yes, uniform mechanisms can be used in many different applications, and I believe that will be a very good topic.
Any more questions?
Okay, so
Yeah.
it's time now, right?
Yeah. Okay. Then
Okay.
we will stop here. Thank
Yeah.
you, Sean, for this evening session. And
Yeah, thank you for everyone's participation. Thank you.
yeah, bye now.
Bye.
I would request Ashish to take over the session. Ashish.
Thank you, Shah. Thank you, Naushad, for your good session. And now we have over with today's session. Tomorrow is the last day of this workshop, so we will start with the same time, 5 o'clock, with the interesting topic of Introduction to Material Subroutine in Abacus by Dr. Naushad, and then we will have regular sessions, and in the end we will have a valedictory function as well. So we
In the
welcome you
validatory
tomorrow.
function, Professor Chamal may engage you for about half an hour, and I requested our head of the department, Professor Shivkumar, who talked to you yesterday, to join at 8:30. So from 8:30 to 9, we'll have a brief session where we expect to hear from you as feedback on how you felt and any ideas that you have with regard to some follow-up for workshop that we plan to have in June. Professor Chamal is likely to come to India at that time. We originally planned to have two levels of offline interaction, one at Chennai and one at Jamshedpur, even this time, but that could not happen because of this, Omicron. So we may do that in June. So if we were to do an offline interaction in June, everything is a follow-up workshop. If you have any ideas of how we should structure it, or any topics that you want to be focused on, you can give us some ideas tomorrow. So please participate in the voluntary function and give us good feedback orally. Perhaps we can even circulate a small
Google form.
feedback Google form where you can also write some of these things verbally. Okay.
Okay. Thank you all.